So the idea of migrating away from the older ways of doing business, the static vision of the world as being flat, into the global environment that we're all working in, and introducing the concepts in geodesy which take us from a vision of the world as a sphere to one that we know is not quite like that and can be quite complex to understand. To also give you the background in fundamentally understanding what is a GPS position. What comes into the process of making that measurement at each and every location? This is quite radically different from previous measurement capabilities, whether it was measuring with a chain, or turning an angle with a theodolite, or measuring with an electronic distance measurer that was using microwave or light wave. Now the relationships between different points are computed through individual independent measurements at equal points, brought together and managed together. And how does that data work? How is it acquired? What are the error sources? How does it relate to something on the ground? Our global coordinate systems. You're using a global positioning technology, yet in many cases you might want to actually portray it in something that's more two-dimensional and very, very localized. So what are the procedures you want to follow to understand that? Understanding the geodetic datums that are associated with it. The multitudes of datums, whether they're national datums for the United States or global datums that might be available. The relationship between mathematical surfaces, such as the ellipse, and the gravity field, such as the geoid. These are new concepts to many users and are vital to understanding and being able to effectively use GNSS technology. How are things moving with time? How will you adapt to those motions? You and your community, your company, your agency. Looking at positional differences that are coming about that are planned for 2022 by the National Geodetic Survey. Lateral or horizontal positions, easily in the looking at changes in the range of a meter to almost 1.5 meters. And heights, the most important aspect of probably our entire national reference frame. The vertical height component. Everything is about where water goes. We see this all the time in the major flooding areas that have occurred in the country, even just recently. And the traditional methods of collecting that data versus more contemporary ways of collecting it, as opposed to using GNSS technology. And bringing that data together in the more complex environment of the relationship of our terrestrial surface, the reference ellipse, and the geoid that helps us model the global mean sea level. So these are the fundamental aspects of the geodesy that are going to be presented in these forthcoming presentations. Again, also looking at the change predicted in 2022 for the ellipsoidal height component. And finally, future sessions looking at factors with GPS, the error sources that will impact GPS measurements, the predictability of using tools such as the NGS Online Positioning User Service, or utilizing some locally available real-time network. Well, just what is geodesy? Geodesy is not a terribly well-known science, but the concept of it is taking what looks like this, the image that many of us have seen of the Earth, pictures taken from space where the Earth is a perfect sphere, or you're used to looking at a globe that the teacher has in school and it's a perfect sphere. In reality, the Earth doesn't quite look like that. It's really a much more disturbed and distorted surface. Now, mind you, this image is somewhat distorted itself to be able to show those changes, but the Earth is not a perfect mathematical surface, and therein lies part of the problem with creating global or even local regional reference coordinate systems, is that the Earth is not a perfect sphere. It is what's referred to as an oblated ellipse mathematically, and we're going to describe how that's defined. But the Earth, because of the underlying nature of our geology, that is mass under the surface of the Earth, it's this bumpy kind of surface. And I'm not referring to the topographic surface that we work on and live on. I'm talking about the average surface of the Earth being affected by local changes in gravity. And understanding all of this, at least at a fundamental level, is vitally important in our use of tools such as the Global Positioning System and those other satellite systems that are now becoming part of the Global Navigation Satellite System Network. Increasingly, as users demand higher positional integrity that these tools can provide, a few centimeters or a couple of hundredths of a foot, it's important to have at least a modest background in understanding the basic geodesy and the process of geodetic surveying. And I'm not going to go into great depth in this particular session on all the individual issues in a datum. I'm just highlighting this. We'll talk about this in greater depth in following sessions. But just a geodetic datum. What is a datum? Coordinates are defined in datums. Heights are defined in datums. And as the slide says, it's just a set of constants. Some set of constants on which we can base our set of coordinates or heights. And these datums are typically given names. I've just listed a couple here. The North American datum of 1983, or NAD 83 as it's often called. But quite literally around the world, both horizontal and vertical, there have been hundreds of datums until the development, the advent of space-based positioning, primarily the Global Positioning System. So it's important to understand what a datum is. Where does it come from? What are the foundational elements of them? And in fact, these are the kinds of things that in advanced degrees are built on, but we're going to try and take it from a fairly modest perspective that, if you go through the presentations we're going to give here, you've probably got about 85% of the understanding about what a datum really is. So we have to talk about datums. We also have to talk about contemporary conceptualizations. And that is, you're going to start hearing more and more about the concept of reference systems, reference frames. These topics will start to be thrown out now. In the geodetic community, we typically talk about reference systems as opposed generally to datums. Now, a reference system, as noted here, is this idealization of the various elements that we want to incorporate in the design, the definition of our coordinate and height systems. And traditionally, historically, if you will, the development of these datums were based on some limited knowledge of Earth orientation parameters. That is, fundamental things like where's the location of Earth geocenter? No one cared before the advent of GPS. Earth orientation parameters such as how the Earth wobbles on its axis. These were elements that were known in the field of geodesy, but had little, if any, impact on the modest activities that people were doing day to day. Well, increasingly, as multitudes of disciplines, not just surveyors and engineers, but many, many disciplines are accessing GNSS technology and they want to get higher levels of positioning integrity, the concepts behind these Earth motions are vitally important to at least fundamentally understand. And some of them we know fairly well, or at least we are accustomed to noting them, such as plate tectonic motions. We know that the plates of the Earth move and cause volcanoes and earthquakes. We're well aware of that, but we often, in many disciplines, don't take that into account in the use of coordinates and or heights. And that's going to be an increasingly important element to understand. How the Earth wobbles on its axis, another element of Earth orientation parameters. And these elements all combine to give us a concept of how we need to define the size and shape of the Earth and how those various agencies around the world, in the case of the United States, the National Geodetic Survey, have to build and design the geodetic datums that support the use of these vital space-based positioning technologies. The reference frames, the current realization deals with a number of different positioning and measurement systems. I'm not going to go into great depth with them here. I'll talk about them in one of the future presentations, but understanding that right now we're dealing with primarily 4 different measurement systems: GNSS, Global Navigation Satellite Systems, which at least right now is primarily the Global Positioning System, the US Global Positioning System; VLBI, Very Long Baseline Interferometry, Satellite Laser Ranging, SLR; and another called DORIS, Doppler Orbitography and Radio Positioning integrated on satellite, as well as traditional leveling. So these are elements from measurement systems that provide us coordinates and orientation data. Much of this is defined through the International Earth Rotation and Reference System Service. Again, I'll highlight who they are and what they do in a future session. But in practice, we take this whole concept of reference systems, reference frames. In general, the user at a practical level, when you hear that, when somebody says reference frame, if it's just easier for you, you can think of it as a datum. It's a more contemporary way of saying geodetic datum. And just to highlight, I'm going to again talk about these in greater detail in following presentations. We're going to talk about horizontal, or now more contemporarily, geometric datums, which are based on 8 basic constants. You see them outlined here. Again, I'm going to go into greater detail in another session. Vertical datums, right? Different types of vertical datums, tidal vertical datums versus geodetic vertical datums. The importance of each one of those and the distinctions between them. That's important to understand as you're collecting or using data. So let's take a moment now to visit the historical development of geodetic coordinate systems. And we need to go back to around the 1730s. A large argument was going on between the French and the English. And this is primarily the Cassinis, the family of the Cassinis, who were, to one extent or another, in charge of the French Observatory in Paris. And the Cassinis, based on data that had been observed in the vicinity of Paris, had postulated that the Earth was a prolated ellipse. That is, it was elongated at the poles and flattened at the equator. While Sir Isaac Newton in England, Sir Isaac Newton, who was not a surveyor, Isaac Newton was a mathematician and a physicist, Newton says, no, this can't be. The Earth spins on its axis. We know it must be an oblated ellipse. That means it must be flattened at the poles and elongated at the equator. So this argument goes on back and forth, and for a number of years. And it's finally realized that, okay, the only way to settle this is to actually go to the field and make some measurements. So the French prepare 2 field parties, 2 field expeditions. The 2 gentlemen that you see on the corners here, La Condamine and Bouguer, they go off to what was then called Peru. It's modern Ecuador. And they are assigned to perform a measurement of a piece of a meridian. Now understand that a meridian is a line going from the North Pole to the South Pole and going through you, right? So they are tasked with going to Peru near the equator, right, and to perform a measurement along a meridian. At the same time, the gentleman at the bottom, Pierre Maupertuis. Maupertuis goes to what was then referred to as Lapland, which is contemporary Finland. He goes off and he's now going to measure the same thing, but closer to the pole. And it's interesting to note that Maupertuis, while he's going to the north, he's up there for about 18 months. Right? That's long enough, it's cold. Whereas La Condamine and Bouguer, who are going to Peru, they're gone for 9 years. 9 years to make this measurement. And there's actually quite an interesting book, The Measure of the Earth. It's a fascinating read about all of the elements that went into this. But nonetheless, they go off for their 9 years. Maupertuis goes off to the north. They return to Paris and present their findings. And what they show, and the image that you see here is a simulation of their perspective on what the Earth looked like. That is that the folks that went to Ecuador are seeing a piece of the Earth measured in toises, which is, in this case, approximately 110,500 meters. What they had seen near Paris was a larger value, and what they see when they go to Lapland is an even larger value. So that means that, in fact, the Earth is an oblated ellipse. It's flattened at the poles and elongated at the equator, and hence Newton wins the argument, if you will. An interesting comment from Voltaire that Maupertuis went to the ends of the Earth to find, which Newton discovered from his desk. I always found that to be an interesting comment. So there we start. Okay, we now agree mathematically that the best mathematical figure to use to define the size and shape of the Earth is an ellipse. Right? It's not a sphere. It's an ellipse. It's flattened at the poles and it's elongated at the equator. But how big is it really? Well, remember, this is the 1730s, 1740s. There are no space-based positioning. So the concept of how big the Earth is becomes very parochial. That is, institutions, organizations around the world go out and start making measurements. And what they find is every place they go, the values are a little bit different. So in defining something as simple as this reference ellipse, how big is this ellipse? Well, let's look at the ellipse itself, and then I'll kind of show you some historical perspectives on that. So mathematically, what we're referring to is a surface. It's three-dimensional, of course. It's flat at the poles, elongated at the equator. And it's defined by really quite a number of different attributes. But what you're going to see here are three. If you know these three, if you know what they mean, you've pretty much got most of it licked. So the idea behind the reference ellipse is that you have a value that's referred to as little a, the semi-major axis, and that's defined as the size of this surface from its center, wherever that is. Right now it's purely mathematical, so that center is not located anywhere. Little b, or the semi-minor axis, or the rotational axis, and here's where the big math comes in. That f, which is the flattening, the ratio of the flattening, is a minus b divided by a again. So fairly simple. But it requires having measurements. And just as an example of what's happened over time, organizations have gone to the field, made measurements in their particular communities, and this is only a portion, a partial list. There are something in the order of about 80 or 90 different mathematical surfaces that have been used. And I've just given you just some highlights here of various ones and their sizes and shapes. Because a field team that might go and perform some measurements on the east coast of the United States would get a different set of values than one that was observing in India or in the UK or in France or anywhere else. So until the development of GPS, GNSS, groups of individual countries and groups of countries would oftentimes use their own local definition of the size and shape of the Earth. It made life very, very complex. Just to highlight, and again I'm going to go into this in greater detail, in the United States we've had 3 different official reference ellipsoids. Bessel, Clark, and Geodetic Reference System 1980, and then the Global Positioning System uses its own called World Geodetic System 1984. Again, I'll talk about those when I talk in the session on horizontal and geometric datums. We also need to understand the surface referred to as the geoid. Now, in the science of geodesy, the geoid is one of the holy grails. Geodetic scientists around the world have been searching for the true geoid for a very, very long time. So what is it? Well, it's really a fairly simple explanation. It is this. It is an equal potential surface to which gravity is normal and very closely approximates mean sea level over the entire Earth. An equal potential surface being one in which the potential of gravity is the same everywhere. That means water does not flow along an equal potential surface. And mean sea level, well, what is global mean sea level? It's fairly, I won't say it's trivial, but we can fairly easily measure local mean sea level at some coastal town, but how do you measure global sea level? This has been a great problem in the science of geodesy. So it's an important element that's part of the geodetic framework. And to highlight it, here are the three surfaces given together. We have our topographic surface, the surface that we live on and work on. The reference ellipse, the line in red, this is the mathematical model for the size and shape of the Earth. And the geoid. And here I've said that's average mean sea level, or in the context of these presentations, it could also be thought of as the surface of the national vertical datum. In this case, for the United States, for the conterminous United States, the national vertical datum is referred to as the North American vertical datum of 1988. It's not mean sea level, but it is the surface from which heights are determined. So it is a surface. It is not a physical surface, as the ellipse is not a physical surface. And we have to deduce their locations through a variety of measurement systems. And this is the importance of understanding the concept of the various elements used in GPS measurement systems to be able to deduce the most important and accurate elements of the geodetic framework. We also have to, particularly looking at heights, and heights are really the most crucial element of all of the geodetic components, and that is the complexity of understanding heights. Again, we'll talk more about some of these in the definition of vertical datums, but understand that once you've picked a surface to which you're going to reference your heights, that there are a multitude of other equal potential surfaces through which the height might have to pass to define your particular location. So it's really important to understand the complexities in determining heights. Heights are the most critical component, I believe, of our national infrastructure, because everybody wants to know where water and other fluids are going to go. And so understanding the fact that these surfaces exist and they have an impact on measurement systems is a vital part of fully understanding the values that you may achieve from GNSS or leveling or whatever the procedure might be. Another part of this complexity, it doesn't come around too much in most contemporary measurement systems, but it's important to know that it exists. And that is issues referred to as deflection of the vertical. Right? So a surveyor goes to the field and they want to make some particular measurements. Maybe they need to establish a reference direction or an azimuth or a bearing. And historically, in a lot of surveying in the United States, the definition of the location of what were referred to as baselines and meridians for particularly the western United States, the public land survey system, were defined by astronomic observations, the determination of latitude, longitude, and direction, or azimuth. And those are impacted by the fact that the reference ellipse from which we are going to compute our coordinates and the geoid, that surface that defines local gravity, are not usually the same surface. And they can have a difference between them. So the image that you're seeing here is, in the case of a direction or an azimuth, I want my azimuth to be defined along or in conjunction with the reference ellipsoid, the red line, but I'm making my measurements with a tool that is leveled to the geoid. So there's an angular difference, a deflection of the vertical. And here you see it purely as a two-dimensional thing. There's actually a north-south deflection and an east-west deflection, and they have important roles to play in this process. But just to understand, particularly if you're dealing with historical data that may have been observed astronomically, that it's vital to have a good knowledge of what these deflection of the vertical components are so that you can bring historical information into a more appropriate contemporary context. Defining those reference ellipses now means we have to have a coordinate system. Now, this is one of the areas in which I personally have found considerable issues with the overwhelming majority of geospatial users. We all learn the fundamental concepts of coordinates, latitude, longitude primarily, probably somewhere in about the 7th or 8th grade. And the teacher came in and held up a globe and defined what latitude and longitude was, and there was a test at the end of the week, and you got it right, and you get a gold star on your forehead, and boom, you forgot about it. Put that in the back of your brain, never had to bring it forward. Well, now we have, again, this multitude of various disciplines who are accessing high accuracy positional technology, and the understanding of how those coordinate systems are different from what we may have learned historically is a vital part of it. So just to highlight here, the foundational value of all positioning that is done with space-based satellite systems, GPS, the Russian GLONASS, the upcoming European Galileo, the Chinese Beidou, is not latitude, longitude, and ellipsoid height, or it's not state plane coordinates or UTM coordinates or some other planar coordinates that you might be using. It is an Earth-centered, Earth-fixed X, Y, and Z Cartesian coordinate system. So the user has to fundamentally understand the relationship of this X, Y, and Z coordinate system to one that might be more appropriate for use in your local environment. That is, how are we making a change from this X, Y, and Z coordinate system that was derived through our GNSS observations into one that is more appropriate for my use? That is, latitude, longitude, and ellipsoid height. And here you see the Greek letters phi and lambda. Those are the traditional Greek letters that are used in geodesy to define latitude and longitude, and or northing and easting, or X and Y coordinates, often displayed as state plane coordinates or UTM coordinates. And as long as user is provided with the appropriate algorithms to go between this, there's no loss of integrity in the data. Finally, adding that last component, the geoid model, that is the model that tells you that difference between the reference ellipse and the geoid, can now provide you with latitude, longitude, and orthometric height, or northing and easting, state plane coordinates, UTM coordinates, and orthometric height. All of this, at least in the United States, all of this was originally defined by Thomas Jefferson. Thomas Jefferson was president in 1807, and he created the Survey of the Coast. Jefferson, being a surveyor himself, he understood the importance, the need for a mapping system for the United States. He created the Survey of the Coast through the Ordnance Act the Global Act of 1807, in which he created this institution and hired this gentleman, Ferdinand Hassler, to be its first superintendent. And here you see a picture of the first triangulation network, which happened to be around the city of New York. The idea that Hassler proposed is that if we're going to make nautical charts that have any validity, that they must be consistent. That is, a nautical chart in Boston had to be in the same coordinate system as a nautical chart in Annapolis, Maryland, or in Savannah, Georgia, or wherever it happened to be. And Hassler was the one who actually began this whole concept of building a geodetic reference frame for the United States. The organization has gone through a number of name changes. In 1970, it became part of the National Oceanic and Atmospheric Administration, now known as the National Geodetic Survey. But it's the oldest science agency in the U.S. federal government, and it's responsibility is to maintain the geodetic datums. Very quickly, I want to highlight just a few images, some slides that are going to show you some of the complex instrumentation that was used in the earliest days. And this is just a primer, if you will, into the types of work that were done and will be discussed a little bit further in one of the other sessions. So here we see the use of geodetic astronomy, the development of instrumentation itself, much of which, at least in the early years, did not even exist in the United States. Agencies like the Coast Survey had to go to Europe to acquire the appropriate instrumentation. Later developments using more modern astronomic observations, the development of latitude observatories, the knowledge that beginning about the 1890s, the understanding that the Earth wobbles on its axis. The Coast and Geodetic Survey, now the National Geodetic Survey, began the process of actually being a part of a global institution that looked at how the Earth actually wobbles and created observatories, one in Gaithersburg, Maryland, and another one in Ukiah, California, that the sole function was to monitor changes in latitude to be integrated into the greater elements of defining what the geodetic network was going to be. The field process that went on, the determination of measuring angles, building towers to get up over obstructions, running levels, the process of actually running levels on the ground. These were all part of the physical framework that the geodetic surveyors had to go through. And what they left behind, and these are an important part of it, I particularly like these. These were flyers that were produced by the Coast and Geodetic Survey and the National Geodetic Survey, often referred to as Marvin Marker. I love the name, but these flyers were intended to give users, a little bit of an understanding of the different types of survey markers that were going to be placed in the ground. As all of these high accuracy data were being collected, horizontal values, latitude, longitude, or height values, as the images that I just showed you can indicate, it took a lot of time. It was a tremendous amount of effort that went into building, physically building these geodetic networks, and you needed to leave something behind, something in place that captured those values. That is, if I determine the coordinates for some particular location through the various measurement systems that I've just shown you, if I don't leave something reasonably permanent behind, then I've just wasted that effort. So the Coast and Geodetic Survey went to great lengths to use different types of markers to indicate the various types of work that were being done. So surveyors are, in many cases, they're very familiar with these, such as a triangulation marker. Got a little triangle in the center, so we know that was it's a mark that was performed or set as part of the concept of triangulation, and it has good horizontal coordinates associated with it. And when they would set those marks, because so much effort was placed into their observations, they would set other ancillary marks, reference marks that would tell you where the primary marker was. Or the observation of high-quality magnetic data, so the relationship between magnetic north in this case, or geodetic north, made by magnetic stations. Again, a function still provided by NOAA, also by the U.S. Geological Survey. The observation of gravity at points. Benchmarks, marks that define heights, accurate heights. And over the years, while the marks have generally remained the same in terms of their size, they've literally exploded across the country. There are hundreds of thousands of these markers in the ground, actually more than 1 million similar marks in the ground from many, many, many different federal, state, local agencies that want to capture and preserve this geodetic information. So when the Coast and Geodetic Survey, when they changed their name to the National Geodetic Survey in 1970, they issued a new set of marks, so there's another set of flyers from Marvin Marker. But it's the concept here, what I'm trying to get across here, is that all of these measurement systems are related to some physical realization on the ground. And that's an important element of understanding the geodesy. Another part is, again, a little bit of the historical perspective. We often think of someone performing some measurements. Maybe it's a surveyor. Maybe you're driving down the road and you see the surveyor who's working in your neighborhood. The vast majority of times, those individuals live and work in your neighborhood. That was not the case with the development of the geodetic framework for the United States. The field units, the field parties that the Coast and Geodetic Survey had, the National Geodetic Survey had, up until the middle 1980s, were actually sort of nomads. Right? They would, here you see a couple of images of them actually living in tents back in the 40s. Later on, getting trailers, moving their families around from place to place, wherever the survey would be conducted. The headquarters would say, hey, we need a survey out in Utah, so the whole field party, which would be somewhere between 25 to 35 individuals, oftentimes with their families, sometimes with kids, right? Haul them all along to the middle of Utah, make those measurements. They would be out there for maybe 2 or 3 months at a time. They pick everybody up and move them again. And so for decades, entire employees of the Coast and Geodetic Survey, National Geodetic Survey, never came into the office. They were always in the field. And it's just a little piece of our history to understand how the networks were defined with these people who spent their entire careers building these networks, living in these kinds of conditions, which very few of us would put up with today. All of the data that you're going to hear about in the coming presentations as part of this series are today part of what's commonly referred to as the National Spatial Reference System. It is that system which brings together all geospatial information. And I don't care what perspective you come from, whether you're a surveyor or maybe you're working with a geographic information system. If you've been to any number of different presentations, particularly on geographic information systems, GIS, you've seen this kind of an image of the layers in a GIS many, 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 many times. What's often not shown in many of those presentations is the geodetic control at the bottom. So I've been to many of these GIS presentations where some kind of an image that you see here on the right side of the screen has presented, showing the various layers that can be in any geographic information system. And there's a multitudes of them, and depending upon the nature of the GIS in whatever institution, organization, community that it's being used in, of course, those layers can easily change. And at the bottom, there will almost always be one that says something to the effect of base mapping. And I've asked many, many presenters at these various conferences, okay, you have a base map, that's an important thing, you got to have that. Where'd the base map come from? How'd you get the base map? Oftentimes it's like, I don't know, it's just there, it's existing. Well, the geodetic control, these monuments in the ground, and whether those monuments take on the size and shape that I've shown you before, or they're in other configurations, nonetheless, all of this base mapping is defined relative to a common coordinate system, which is the geodetic control. And this National Spatial Reference System, defined by the National Geodetic Survey, that agency part of NOAA, the National Oceanic and Atmospheric Administration, has to be consistent. And the goal of the National Geodetic Survey is to provide to the public latitude, longitude, height, anywhere in the country. That's from Maine to Guam, or from Alaska to the U.S. Virgin Islands, accurate to just a couple of centimeters. Anywhere, anytime. That's the goal. So whether you're using latitude, longitude, state plane coordinates, UTM coordinates, whatever, lat, long, height are the important elements that the vast majority of spatial data users need. It's data about scale, gravity, and orientation that are important for the geodetic institution, National Geodetic Survey, to be able to define. And increasingly, This is the fun one. How values are changing with time. Remember, I pointed back in one of the earlier slides, I had a little image about plate tectonics. And we all know it exists. And in many cases, you live on it. If you live in California, Western Washington, Oregon, Hawaii, parts of Alaska, you are well acquainted with dynamic changes in the Earth's crust. But the vast majority of the country is not. And surveyors and others across the country have, to a great extent, dealt with the Earth as a static body. Well, now that we are embracing high accuracy positioning at the couple of centimeter level, using a global positioning process, we now truly must get in touch with the fact that coordinates changing constantly, even in areas such as Iowa, for example, in which it might be tectonically boring. That is, there are no big earthquakes, none of that's going on. But nonetheless, all of the plates of the Earth are moving, and if we're going to demand the use of high accuracy positioning at the few centimeter level, it's in the very near future, very likely, we are going to have to start dealing with the fact that we have coordinates that are only valuable for some particular epoch of time. And they might have to be reobserved or re-realized at some later point in time. So that's an important element of this National Spatial Reference System. The system also has a number of components, and I think this is important to realize, that these components include 4 primaries. There's a variety of others, but 4 primary. One is the national shoreline. So the Coast and Geodetic Survey, the Coast Survey was originally defined in 1807 to produce the shoreline, to produce the nautical charts that were so vital to the country. And they are still produced by NOAA to this day, an office known as the Coast Survey. And they're located in Silver Spring, Maryland. They're partnered with the National Geodetic Survey. And a variety of different measurement techniques are used. And the slide here shows primarily the more contemporary ones of remote sensing, whether it's LiDAR, or spatial imagery, digital imagery. But I also include the older picture of the gentleman out observing with what's known as a plane table. So the shoreline of the United States originally was observed manually by the process of plane table surveying. And they performed some rather very, very high quality information, much of which is still used to this day to look at shoreline change mapping. So that's an important critical element of the National Spatial Reference System. But very likely the one element that most users, and in this case probably mostly surveyors, are familiar with the National Spatial Reference System is this: a network of geodetic control points. Permanently monumented, although we got to understand there's nothing permanent, but they are passive. They don't do anything. Right? And the marks take on a variety of sizes and shapes. And these go back to the image that I showed you previously, the little flyers called Marvin marker, the different types of markers. What you're seeing here are just a few images of some of my personal favorites. Poured in place concrete post with a brass, bronze, or aluminum cap on the top. Or a chisel square. This one says benchmark A. I particularly like that one. That was the primary benchmark or height of the United States. 1877, a little place called Hagerstown, Maryland. And from there, the Coast and Geodetic Survey began leveling across the United States. It's still in place today. You can go and visit it. Stainless steel rods driven to refusal, very, very high quality monuments. Or this one up here happens to be the Body Island, North Carolina baseline. It's a granite pillar that was placed in the ground, 1848. So the images, the markers that are part of this have great history. Not only do they have positional history, but they carry with them the history of the people who designed this and who developed these networks. So, if you ever happen to be in the area of Body Island, North Carolina, the Outer Banks, you can go and visit, this monument, and understand you're standing in the same place that those surveyors were in 1848, measuring this baseline that was such an important component. Now, that being said, This is the historical way in which the geodetic networks have been understood. Some people often like to use the term realized. Right? So if I have a datum, I have a horizontal datum or I have a vertical datum, how do I get them? Where do they come from? Well, I have to have this set of monuments from which new measurements can be made. And this has been the classical way of providing that. That being said, they're very problematic. A, they're passive. They don't do anything. Right? They just sit there. So you come in, you make some measurements, you determine the height or the position for something, you make those measurements, you go away. What happens next? Do you know anything about what's going on at this monument once you've driven away? No. And the values that are produced and maintained and published by the National Geodetic Survey, in many cases, for monuments just like these, could easily be 50, 60, 70 years old. Nobody's been back to validate them. So we don't know if they've moved. And many monuments move for a variety of reasons. They get disturbed or destroyed, there's vandalism, there's natural motion, earthquakes, post-glacial rebound, natural subsidence. There's a whole range of things that can impact the values that are associated with it, whether it's horizontal or vertical. In addition, one of the things that I personally found during my career, the National Geodetic Survey maintains a database with about 1 million of these, but invariably we never put them on somebody's job site. They were always somewhere else. You had to go and find them. They were never exactly where you needed them. Right? So that was one problem. So not being able to ensure that they're well validated, because there's no mechanism for institutions like NGS to go back around the country and periodically revisit each and every one of these. There's over 1 million in the NGS database. It's just impossible. It just never happened. So that's been a problem with positioning. Along comes GPS, GNSS now, and we enter into a whole new dynamic. While at least initially we started with, and still continue, the National Geodetic Survey still continues to publish and maintain data on multitudes of these passive control points. But beginning in the early 90s, we start to see the development of cores, continuously operating reference stations. And today, this is really the foundation of the access to the reference frame. And these cores, just like the passive control, take on different sizes and shapes. So here you just see several examples. The National Geodetic Survey maintains information on well over 2,000 of these around the country, but it's also important to note that of those 2,000 that users can access from the National Geodetic Survey, the agency itself only owns maybe 30 of them or 40 of them. The rest are owned, maintained, operated by a multitude of federal, state, local, private sector interests who all see the value in GPS and collaborate with NGS by building the stations to NGS specifications and then providing access to the data so that NGS can turn around, put it in a common framework, and provide it back to the public. And some well-known institutions here are the Coast Guard with their national differential GPS network, the FAA with their wide area augmentation system, which is another. Many state DOTs do this, and quite a number of private sector companies provide their data. Now, the important difference, major important difference between the passive mark that I showed you previously and these cores are, first of all, the passive marks, if you want to use them, you have to go there. You have to find the mark. You have to put somebody in a vehicle and send them down the road to find the monument. Hopefully it's still there. With the active control, the cores, you never have to go there. Sometimes you can't go there. Sometimes they're in a secured location. And if you do go there, well, okay, now what? You stand there, you look at the station itself, and well, that's very nice. So it's like watching paint dry, or it's like watching grass grow. You're not going to do anything with it. The nice part is, you go to wherever your job is. You set up a GNSS receiver, you make some measurements, and now there are a variety of ways in which you can take your data and process it with respect to this nationwide network of active stations. And there's a multitude of those. And there will be a session on how to process GNSS data as part of this series a little bit later on. But one of the things that's important to note, remember I said with the passive control, the monuments oftentimes are moving. Whether it's local motion, you have subsidence, or you have uplift, or you have some other significant tectonic event, or even something as big as a hurricane moving the monuments. We have no idea how much those monuments have moved unless someone physically goes there and makes a new measurement, is able to report that back and incorporate that data into this national reference frame. With the Corps, they're operating 24 hours a day, 7 days a week, 365 days a year. And some of them collect data at 1 second intervals, 5 second, 15, or 30 second. Typically 30 second is the more preferred. But if one of these stations moves, we know about it. If there's been some dramatic event, we know virtually instantaneously that that station has moved. In addition, looking at things like plate tectonics, the gradual change in, let's say, the North American tectonic plate for Iowa that I mentioned previously. How much is it moving? Well, we know how much it's moving because having these stations in place in many cases for well over a decade, we're now able to incorporate that data into a global management system and be able to detect how much the various plates of the Earth are actually moving. And then that data can now be incorporated into the development, the design of this geodetic reference frame that I mentioned previously. So the future especially is going to take on another dimension that many people are not used to. In general terms, most of us are used to three-dimensional control: latitude, longitude, or northing and easting, and height. Now it's going to have time. How much things are changing with time. And this is going to be a very, very critical part of this element. Now, one of the nice things about this is this institution, the National Geodetic Survey, really tries to stay on top of this game. And as part of these elements that I've shown you, the national shoreline, the passive marks, the active marks that you see here, they also provide all of us with a great array of utilities that we can use, models and tools. And so on their website, they have a series of geodetic computations that you can easily access to be able to do things like apply a geoid model, or perform a datum transformation, or to compute how coordinates are going to change with time. And a variety of these will be discussed in the upcoming presentations. But it's important to note that this National Spatial Reference System, I gave you some of that little historical perspective, which I'll further expand on in the other presentations. But just to understand that this collection of 200 plus years of data now being considered as a single system that's comprised of the definition, the mathematical definition of the size and shape of the Earth, the location, the realization of this vertical surface, the geoid, the implementation of a process by which you can access it, passive and active control monuments, and now models and tools so that you can integrate your data more freely. And so many of you may be using these models and tools and other packages that are provided by a variety of other vendors. That goes on all the time. Just make sure that whoever you're acquiring your information from, that you're able to ask them, their technical staff, are you using these various geodetic computations as they are provided by the National Geodetic Survey? That's the end of this initial